Welcome everyone, I am Vishwamitra Ghosh. I am a postdoc at Max Planck Institute for Software Systems. Today I am going to talk about our recent ICLR paper where we discuss the logical consistency of language models in fact-checking. Language models are impressive at general language understanding. However, they can suffer from inconsistency. In general, if an LLM hallucinates, then inconsistency is a simple test for hallucination. So, what is consistency? Before our paper, most existing related works they were thinking of consistency in terms of paraphrasing. So let's say we have two sentences. Berlin is the capital of Germany, and Germany's capital is in Berlin. And given this sentence, the LLM will say yes or no, just for simplicity. Now, existing notions say that being consistent means giving semantically similar prompt, the LLM will also output semantically similar response. In our paper, we are extending the idea to a more general setting, more specifically on assessing logical consistency of the LLM. So here the idea is that if the input prompts are logically equivalent, then the response should be similar. But if the prompts are different, then the response should be different. So for example, let's say we have two sentences, both are negation with each other. Berlin is the capital of Germany, and Berlin is not the capital of Germany. So you can think that here a consistent LLM should generate response that are negation with respect to each other. Now let's take a conjunction query where we have two subqueries connected by logical AND. For example, Berlin is the capital of Germany and US Embassy is in Berlin. So here we can say that the LLM is consistent with the conjunction query if the LLM gives the same answer if the LLM, when asking the answer on individual queries and taking their conjunction, results in the same consistent response. So in our paper, we are extending the assessment of logical consistency on queries that contains all the primitive operators like negation, conjunction, disjunctions, and so on. And more generally, as a specific test bed, we are considering the task of fact-checking in a knowledge graph using an LLM and then checking consistency in that specific task. So we have threefold contributions. First is benchmark, where we realize that there is no dedicated benchmark for testing the logical consistency of the LLM. Therefore, we are converting existing knowledge graph based benchmarks to consistency benchmark. And secondly, we provide measures for assessing consistency by following the semantic of formal logic, and we soon realize that the existing LLMs are not fully consistent. Therefore, finally, we demonstrate ways in which we can improve the logical consistency of the LLM. Let's briefly show you the framework where we are considering the LLM as a fact checker. So here, in the input, we have a fact that we want the LLM to check against, but it is possible that the LLM does not have the required knowledge to answer this query. Since our goal is to test for consistency, we don't want to consider the case where the LLM is even inaccurate. Therefore, to answer this particular fact or to check this particular fact, we are also providing necessary subgraph from the knowledge graph that are required to sufficiently answer this fact. Now, what are the measures for consistency? Here we are defining consistency in a more abstract way where, let's say we have a given query P and the LLM is consistent with respect to negation operator if the LLM's response on negation of P is equal to LLM's response on P and then applying negation on the response. And similarly, when the query is P or Q, then you can naturally apply the LLM on the individual queries P and Q separately, and then apply the logical OR operator. So essentially the idea is that we want to first apply the LLM on the initial query, which could be conjunction or disjunctions or even DNF form. And secondly, we will apply the LLM on the constituent atomic queries. And we'll say that the LLM is consistent if the LLM's response on the complex logical queries is equal to the LLM's response on the individual atomic queries, and then applying the respective logical operators. Logical consistency can also be extended to not only queries but also logic rules, for example, commutative law, associative law, distributive law, and so on, even first order logic. So check out the paper for the list of constants that define what is logical consistency. So let's now show you some experimental results. Here we are considering Llama 2 13 billion model, and we are considering 3 different data sets and 3 different query types like simple, negation, conjunction, and disjunction. And here we find that the LLM are not fully logically consistent. So here all these numbers, if they are close to 1, then that means the LLM is fully consistent. So we find that the LLMs are not only fully logically consistent but also less consistent when the query complexity increases. Then the question is, how can we improve logical consistency? In our paper, we have tried both instruction prompting, but we find that instruction prompting is not always effective especially on smaller models. And there we have proposed instruction fine-tuning. So the idea is that the LLM will be logically consistent if it is also accurate. So this is like achieving consistency by being accurate. And these are basically the sufficient condition for achieving consistency. So more concretely, an LLM is consistent on a simple atomic fact if it is accurate on the fact as well as its negation. And more generally, if we have a DNF fact, then the LLM is consistent if it is accurate on the DNF fact as well as all the constituent atomic facts. So now, after applying this supervised fine-tuning, we see that not only accuracy increases but also consistency increases in all the cases, which are shown in the bold number. In addition, we also see that here we are only fine-tuning on the previous dataset, but the fine-tuning can also generalize to other datasets like NEL and Wiki. So to conclude, our takeaways from the experiments are the following. We find that the LLMs by default are not fully logically consistent yet, and consistency decreases as the query complexity increases. We can apply both instruction prompting or instruction fine-tuning. We find that to improve consistency, we find that instruction prompting is only effective on the larger models, but on smaller models we need to apply instruction fine-tuning. And finally, we find that this instruction fine-tuning can also generalize to other datasets as well as queries containing more logical operators. And finally, we demonstrate that fact-checking in the context of knowledge graph and LLM can be a very effective benchmark to test LLM's logical consistency. So to conclude, we demonstrate that logical inconsistency is still a critical problem in LLM, and we provide way to assess logical consistency as well as ways in which we can improve the logical consistency of the LLM. Thank you so much.